Adapt. Okay, well, thanks, Sarah, for inviting me to the seminar. I've been trying to attend some of those, but until, as Sarah mentioned in email, I just recently retired from the survey. Until this past summer, sometime too often my job got in the way of actually attending seminars like this. So I've been more steady in this past fall. Okay. Okay, there we go. So I'll be talking about Northern Cordillera. This is a map I think most people here would be familiar, so I won't dwell on this one too much. I'll jump into the more simplified version where we can group all the terrains of the Cordillera into a fewer number of blocks or super terrain, if you want to call them that. And I'll just put the obligatory slide that to show that basically the larger division is this dotted line where most of what we see in Alaska and the coastal BC and Alaska is exotic. And by this, I'm looking at Devonian and older basement to these terrains versus everything that's further east, or not everything, but most of what's further east is not so exotic from Western Laurentia. So today, what I'll do is I'll talk about the intermontane terrains, so the ones that are right in the middle of the origin. And specifically, I'll be focusing on the intermountain terrains in Yukon and part of northern BC. I'll jump a little further south on a few points, but I'll mostly be focusing on my personal experience or my experience with working with some of the people here in Yukon and what do we see in Yukon and how does that inform the Mesozoic tectonics of the intermountain terrain. So, as said on the slide here, most of intermountain terrains in Yukon are represented by Yukon terrain, a series of island arc of mid to late Paleozoic age. That's overlap or in part overlap by Stikina, and further south in BC we have Quinalia. Those are two late Triassic to Jurassic arc terrains that are pretty extensive. And then the core of this set of terrains, we have Cache Creek and then the newly redefined Atlan terrain. So I'll cover a little bit the background on what these terrains are. And then the other thing I will talk about is the Jurassic magmatism that we find in the intermountain terrains in Yukon and northern BC. And toward the end, I'll talk a little bit about the work we did in the Whitehorse Trough, which overlaps all of the intermountain terrains in Yukon. Uh, I will take one zoom out here. It's important to note that the Jurassic plutons, and in this, I'm excluding everything that's southwest of the Denali Fault, that are the Jurassic plutons we find in the insular terrains, which are usually more late Jurassic in age than, so younger than the ones we see in the intermountain. But I think it's important to note that those Jurassic plutons, they occur in the intermountain terrains and not in the North American or the continental margin strata. So that's a major distinction between the two. And with this slide, I also want to highlight that we truly adopted the suggestion by Cynthia Dussel-Bacon that much of East Central Alaska is actually continental margin, paratoctonous continental margin rocks that are more akin to Selwyn Basin than they are to the younger part of Yukon terrain as we see in Yukon. I've also noted here, and I'll talk more about this part here later in the talk, but this was all exhumed in the Jurassic, whereas most of this here was exhumed in the Cretaceous. So it's fundamental, important difference. This is about the only thing I'm going to say about Alaska in this presentation today. Okay, so as I said, most of the intermountain terrains in Yukon are represented by Yukon terrain. That's mostly a Paleozoic history. relating to opening of slide mountain terrain, development of arc complexes, and then closure of the slide mountain terrain in the Permian to Triassic. I'm not going to get into that story. That's a completely different story. The main focus on Yukon Tana in this presentation is going to be its relationship to the Triassic Jurassic rocks and its involvement in Jurassic deformation in the northern Intermontane Terranes. Okay, so we'll start in this part. I don't have a huge personal familiarity. We did a little bit of work in around the Atlan terrain and Cache Creek, but I'll talk a little bit about them so that we're all on the same page as to what they represent. So the Atlan terrain, as I said, so this was first defined like 50 years ago by Jim Munger, but then it found itself kind of incorporated and it was part of that Cache Creek complex, and is considered to be some mafic component in the Cache Creek complex. More recently, colleagues at the GSC, Geological Survey of Canada, have kind of made the point that this was probably a separate terrain, a primitive arc terrain, which is mostly early to middle Triassic in age. And in Yukon, it's mostly represented by what we call the Joe Mountain Formation, which is this general area here. And here's a sample. This is not all the geochemistry that exists from that, but some of the data that we've collected some years ago in this part of the area. So pretty classic on arc tolite type of signature. So these rocks, they overlie the main part of Cache Creek terrain, which I'll talk in a few minutes. I'll cover in a few minutes. And they're imbricated with the Stickinia rocks and Whitehorse Trough rocks. This is some cross-section from a master student that worked with me some years ago. Okay, so to look at some of those rocks, this is a pretty classic Joe Mountain Formation basalt. Some of the volcaniclastic rocks that are associated with that, with unimodal peak at 245 in this particular sample. The other component, if I go back one slide, is these ultramafic complexes that are found in this part of the Atlan terrain. And those have been studied in good detail by Adina Bugatu, who did a PhD. She just defended recently, about 6 months ago or less. And she studied the ultramafic complex and made a really good case. That's a very nice paper she has in Litos, that those were probably in place as oceanic core complexes at about 250 to 245 MA. Okay, so to jump into the main part of the Cache Creek terrain, in Yukon, we don't have a lot of Cache Creek terrain. So basically, the bottom of this map here is the Yukon BC border. And most of what we see in Yukon are large limestone massif, of mostly Permian age, Pennsylvanian to Permian in age. They're associated with alkali basalt that are shown here in this kind of different shade of green here, I guess. And those are collectively, this has been interpreted as oceanic seamounts, where seamount complex that were later incorporated in the subduction complex of the greater Cache Creek terrain. There's a little bit of ribbon chert here and there that we do see in Yukon. This is more common in southern BC. And then the youngest part of this is kind of rhythmically bedded chert argillite and greywacke that extend into the lower Jurassic. I think the youngest ages here are Toarcian in these sediments. I'll jump a little further south in BC because that's where the Cache Creek is really better defined. And the Cache Creek, where you can see those kind of exposure, it is a melange. It's really a subduction complex type material. In central BC, there are Triassic blue schists. As we get closer to Yukon, the blue schists are dated at 174. They're Middle Jurassic or late. I guess it's late, early
Hello.
Jurassic. Hello.
Yes, it is. Hey, Chad.
Okay. Uh, so, uh, so anyway, this is just a map showing some of the relationship around Pinchy Lake, where some of the blue schists have been documented. So, different tectonic slice incorporated into this accretionary complex of the Cache Creek terrain. Okay, moving on to Stikina. So Stikina has in Yukon has a Paleozoic basement. I'll talk about that briefly in the next couple slides. But the bulk of Stikina, and that applies to all of Yukon and all of BC and Yukon, the bulk of Stikina is represented by mafic volcanic, basalt and basaltic andesite rocks of Carnian. Some of them might sneak up into the Norian locally. And that's overlain by a sedimentary sequence, which has limestone members and also epiclastic and other marginal clastic deposits. All of that is overlain unconformably by the Labarge group, which is the main unit or D unit defining the Whitehorse Trough, and I'll come back to this in a few slides. Okay, so before I go talk about the Triassic and Jurassic rocks, I'd like to take a minute just to examine or just to highlight the fact that Stikina, the late Triassic arc terrain, which is very extensive throughout BC and into Yukon, it sits on different Paleozoic basements. So there are different character to these basements in various parts of BC where you see beneath the late Triassic. And I'll focus here, if we look in this part of Yukon, the late Triassic intrusion that are interpreted to be feeder to the late Triassic volcanics. They have same chemical characters. They intrude into Yukon Tanner rocks. So this Mississippian ortonite is a run-of-the-mill ortonite that you find in Yukon Tanner terrain. In this part here, it's intruding into amphibolite and mafic metavolcanic rocks and Mississippian ortonite. Elsewhere in Yukon, so now I'm looking into this part. I was looking at intrusion into this area here at first. Now we're looking into this segment here. We have an entirely different package, which is equivalent in age to a lot of Yukon Tanner terrain, but we don't really know its relationship with respect to Yukon Tanner at this point. The lower part is a Mississippian basaltic E-morb to N-morb kind of signature, probably some sort of ocean floor that's overlain by a sedimentary sequence with volcanic clastic rocks. And importantly, it has Permian limestone with McLeod fauna type fusilin that aligned it very well with the Klamath and other marginal Laurentian terrain, arc terrains of the time. So some of the photos of what some of these rocks look like here. Okay, on to the Triassic. So the Triassic in Yukon of Stikina is represented by the Lewis River Group, which comprises a lower part of Carnian to Norian calcalkaline augite ferric, locally plagioclase ferric, as shown in this photo here, basalt and basaltic andesite. And that's overlapped by various clastic and carbonate rocks. The carbonate, the interpretation has been put out there that they may represent atoll reefs, so that post-volcanism, you have that development of these reef complex on top of the extinct volcanoes. So some of the rocks, what they look like, this is sort of a rather deformed version of the Povoas. Generally, it's not that deformed, but that was one of the best photo I had to show you. And then some of the organism in the reefs and these kind of fascies, which in places have been interpreted to be lagoonal and coeval to some of the reef complex in the Northern. So the chemistry is calc-alkaline, but still very primitive arc signature. Okay, the point here is the distinction between Quinella and Stickinia. So some of the rocks I'm talking about, the Lewis River group, the Povoas Formation particularly, is equivalent to what's been called in northern BC would be called the Stuhini. If you go a little further south, that's called the Takla group. And that looks very much the same as if you were driving through southern British Columbia. You'd find a Nicola group, which looks very much the same, is the same age, similar kind of stratigraphy. So one of the original observation was that, well, we have two arc terrains of upper Triassic age, which are very similar, and the only clear distinction was whenever you could find the Cache Creek terrain in between the two. When you carry this further north, eventually you lose this Cache Creek terrain, and it's been a problem to identify what is Quinella versus Stickinia when you get into Yukon. The same problem occurred here in central British Columbia, where parts of Quinella and Stickinia are both assigned to the Takla group because the early mapper went across this fault without recognizing the distinction between the two. So we've kind of struggled with this in Yukon, and basically, and this is my struggle perhaps, but we basically took on that the distinction between these two terrains in northern BC is what's called the T-Bear fault, which juxtapose Quinella rocks against Cache Creek, and the extension of that structure into Yukon is the Teslin fault. So for many years, I've shown a terrain map that looks like this, where the Teslin fault was the distinction between two very similar looking package of rocks. With more recent work, I've come to realize that this was wrong. Essentially, we have no Quinella or no Triassic Quinella in Yukon, and this was influenced for one thing by this is a seismic line that we shot across Whitehorse Trough. So this was an oil and gas project back in the day. And this is a reinterpretation by Andy Culver that was published in 2017. And along with that, we did gravity inversion. This was done by Nathan Hayward at the Geological Survey of Canada, where we had a really good correspondence in the geophysics between gravity inversion and the seismic, to the point that we feel relatively confident that this is the kind of interpretation that's most reasonable for that part of Yukon. But one of the key findings is that the main structure here is not the Teslin fault, which is here, but it's the Big Salmon fault, and that's the one that distinguishes most significantly the different crustal blocks in the area. So I'll come back to that. The other element that really kind of made me realize the distinction is when we looked at the plutonic suite in the region, and that I'm coming to this in a slide or two. So this kind of structure, Andy was suggesting or wanted to interpret as a flower structure, which is kind of consistent with some earlier work that I did, which was strictly based on mapping structures in the Whitehorse Trough, which is the yellow area in this map here, and just recognizing that this style of structure was probably more consistent with dextral transpression than anything else. The Big Salmon Fault is not shown here because I hadn't recognized its importance at the time, but it would run about here. Okay, on to the magnetism, late Triassic to Jurassic plutons. Uh, so earlier on, we're chit-chatting about some mineral deposit stuff in the Yukon. Being a Yukon Geological Survey employee for many years, that it's always been a backdrop of my work was to be helping mineral exploration in Yukon. And we got a project going looking at Jurassic plutons in Yukon, mainly because those plutons are big money in British Columbia. Like all the dots and squares here are either advanced project or active mining project in British Columbia. And the question was raised as to, well, we have the same age plutons in Yukon. Why don't we have all those big porphyry deposits that they find in BC? So we set out to basically, it was Patrick Sack and myself at the YGS set out to basically visit most of the Jurassic plutons we have in Yukon to try to better understand what they represent. Uh, so just as a quick picture, this is some of the copper ore. We did have one operating mine that just recently closed in central Yukon. This is what the ore looks like, which is not your typical porphyry deposit. Uh, I put this slide in here. So this is the oldest plutonic suite, which is sort of the feeder to that Povoas, the Lewis River group of Stikinia that I mentioned earlier. Just to show that I showed map relationship where this intruded into Yukon Terranes terrain, in this part of Yukon. This is further south here where the same intrusions are intruding into the argite-ferric basalt at that point. I'll mostly be talking about the younger intrusion. So one of the things we did is a lot of precise dating. So this is all CATIM's data that we did. And so just to orient yourself a bit here, this is a restored, somewhat of a paleospastic map. So let's say this is the late Jurassic to earliest Cretaceous snapshot of what the arrangement of terrain. So I've restored the Tintina Fault here to restore this part of Yukon terrain where it probably started. And I also kind of put some restoration on the Big Salmon Tasman Fault system here to realign things as to how they might have looked like in early Cretaceous. So one of the early observation or one of the obvious thing to note from the dating is that we have a southward progression of early Jurassic plutons on the west side of the Big Salmon Tasman Fault system. We don't see this same kind of progression when we look on the east side, what I called here the Locken Suite. It doesn't have that age progression. The Locken is also distinct in that it's a pyroxene bearing, diorite, monzonite, granodiorite type composition, whereas when we're west of the Tasman Fault, this is all hornblende biotite bearing granodiorite to granite composition. And then I'll just point this out here, the youngest suite. I'm not going to talk about this McGregor. That's an odd Pluton on its own, so I won't dwell on that one. But this younger Bride suite is coming into Cache Creek, Stikinia, and Whitehorse Trough. So it stitches everything else, all these other elements by 174, 172, 168. So okay, so the only geochemistry really that I'll look at on these plutons is looking at some of the isotopic data. And so the top two plots here are whole rock isotope anchored with the CATIM's dates. This is laser data from zircon in those plutons. The key thing is to see that as you go to younger ages, to younger plutons, we see an increase in crustal contamination into these plutons. So we start from relatively juvenile to, somewhat evolved by, about 185 or 180. At 174, there's a sharp break, and we return to more juvenile value. And this is this bright sweet that I was mentioning, which is here in the middle uh, of the Intermontane Terranes here. We don't see quite as clear of a pattern. It looks like it might be a reverse pattern in the Lock-in Suite on the other side of the Big Salmon Tasman Fault. But it's not, it's not as many samples. It's not as clearly defined as what we see on the west side. Okay, the other thing we did with all these plutons is wherever the composition was suitable, we did aluminum hornblende barometry in the plutons and and found that the earliest, the Minto Suite, the latest Triassic to early Jurassic Minto Suite typically had pressure of crystallization in the 5 to 7 kilobar range, and as we go younger, we see lower and lower pressure up to the Bright Suite, which was probably in place at relatively shallow level. Some of the rocks, this is a fairly typical. I've shown kind of an undeformed version of the late Triassic, but most of the late Triassic plutons that we see, the feeder to Stikenia, volcanic arc, are of that state of deformation. That's pretty common. The early Jurassic Minto Suite locally is quite well deformed, has a ductile fabric like we see here, but it's commonly not deformed and looks pretty happy like this. This is kind of syenite is a more of a rare component, but there are locally these really coarse-grained, beautiful looking syenite. I also put in a quick, just as a little snapshot, that the Minto Suite commonly has a magmatic epidote, which has been, suggested to relate to pressure in the 6 kilobar range before. Now, a lot of people are a little skeptical about aluminum hornblende or magmatic epidotes, so to reassure you that these are realistic numbers, the bold numbers here, so all the circles in here are the results of that aluminum hornblende, but we do have other studies that have also looked at regional assemblage in Yukon terrain, and the 5 to 7 kilobar in the early Jurassic is pretty common. So here's a plot of some of the better results from thermobarometry. So it's a pressure time plot. And you can see that, the bulk of the samples are in the 5 to 7 kilobar range between 200 and 185 million years. Typical fabric in Yukon rock, anybody who's worked in Yukon terrain will recognize this kind of fabric as being pretty widespread. Now, the other map I have here are mica cooling ages, so I didn't discriminate here. This is a combination of both biotite and hornblende. So let's say closure temperature is somewhere in the 300 to 400 degree C. So let's say that all the yellow circle here are really representing samples that were cooled in the Jurassic. So next slide, I'll jump into, you can see this hatch pattern where I say cooled in the Paleozoic. Well, we'll go have a closer look to a relationship around this area here. So this is a snapshot from the Yukon geology map. This is an area where we were able to map a Mississippian granite. This is what it looks like. With Mississippian cooling ages in this region here, that's juxtaposed against an amphibolite facies Jurassic domain, or domain that cooled in the Jurassic. in the footwall here, and that's what some of the rocks look like in the footwall. So this is sort of an indication that at least some of the exhumation that we document in the Jurassic uh, was tectonically driven. How much of it we don't know, but we do have this relationship here that tells us that there were extension faults facilitating that exhumation in the Jurassic. So in essence, we have burial to 5 to 7 kilobar in early Jurassic, which was followed by exhumation shortly afterward, still in the Jurassic. Okay, so I will talk a little more about the mineral deposit that we have in Yukon, partly because that's what gave us the money to do the study, but it's also because I think that they're providing compelling evidence for the story I'm building up here. So there's the Minto mine, which was in production until I think a year and a half ago is when they shut down. And the Carmax deposit, which is an advanced exploration project, has not seen production yet. So the ore at the Minto mine, this is what it looks like. It's basically these gneissic bands, like in cross section. That's what it looks like. Every red area is just one of these gneissic band hosting copper mineralization, and everything that's in white around it is just happy, uh, good looking granodiorite, also of early Jurassic age. Although I'm jumping ahead here, we assumed that this was early Jurassic, but I'll come back to this. Again, some what the ore looks like in this deposit. The other deposit to the south, Carmax, that I mentioned before, we had a master student, Nicolette Kovacs, did a really nice job there at mapping the occurrence there. So all the red bands here are rafts of amphibolite that are engulfed into a younger granodiorite host. And then particularly Nicolette was able to do really nice detailed work to show that the progressive migmatization of some of these amphibolite drafts. So this is what the ore looks like at the Carmax deposit, and some of the documentation of the migmatization that she was able to document there. If you look at the ore in thin section, this is what that looks like. This kind of texture really tells you that this was a sulfide melt that produced this mineralization, and that led to some suggestion from earlier study that maybe perhaps this was a magmatic sulfide system. The key to answering what those deposits was came when Nicolette was able to extract zircon out of one of these amphibolite rafts, which was quite a feat to find good zircons in there. But when I say good zircons, that's what they look like. They're pretty, for all intent and purpose, they're pretty ugly. So we got this sample, and I worked with Jim Crowley at Boise State to try to see if we could crack the complexity of these zircons. And Jim didn't give up, and he actually, we got the answer. So he did an incredible amount of laser dating to document various age populations in those zircons. And then he went into what Jim did is that he basically polished zircons on both sides and identified domains of homogeneous composition and ages, and then used a laser to cut those fragments so we could go into the CA TIMS with that. And it worked out wonderfully because we were able to identify all these different population with CA TIMS, dating the protolith probably at around 218 ME, and the main phase of the batholith was probably about 200 with a migmatization event at about 196. Nicolette also documented 2 generations of molybdenite in this ore. and basically an early phase that looked like it's kink, anhedral, and deform, and a younger euhedral phase that's in with this mesh, the mesh texture sulfides. She did, I think it's 4 samples with rhenium osmium dating and got a spread of ages between 213 and 198. With Molly dating, it's not a single mineral age, it's a mix ages. So we think this is closer to the age of mineralization, and that's probably representing this recrystallization event, the magnetization event. Okay, that's it for mineral deposit. We'll just have a quick look at the Whitehorse Trough.
Recording in progress.
Okay. The Whitehorse Trough, as I said, is unconformably on top of overlying the Lewis
Actually,
River.
hold on just a second, Mo. Nobody else should be recording this talk because that wasn't my computer. Sorry to interrupt. So please, I'm making a recording. I don't think anybody else should be able to record it because I'm the host. But anyway, just wanted to make sure that everybody realizes there will be a recording, but please don't make your own. Okay, sorry to interrupt. Let's continue.
No problem. Okay, so Whitehorse Trough, it's basically there are two formations, I'm saying in quotes, because they're really lateral facies. There's a northern facies of more shallow marine deposits and a southern facies around Whitehorse area proper, which is more of deep water deposit. The two are pretty well tied because there happens to be pyroclastic deposits that we find in both the shallow marine and the deeper marine deposit. And this is one photo of these Pliensbachian pyroclastics. So to look at what those rocks look like, this is sort of the northern part of Whitehorse Trough, shallow marine, probably a deltaic type environment here with sandstone and conglomerates. Further south, we have this kind of rhythmic sandstone, mudstone couplet turbidites. And within this backdrop of turbidites, we do find mass flow conglomerates in places. There's been a couple good studies that were done over the years looking at counting clast in some of these conglomerates, and I'm showing here one. This is from northern BC, but we see the same around Whitehorse area, where the older conglomerates are more dominated by sedimentary and volcanic clast, and as you go up section, you see more plutonic clast, and the youngest conglomerates, have a significant content of metamorphic clast. Here's a Torakian conglomerate from near Whitehorse. So this is a clear indication that we're having exhumation and we're dissecting that late Triassic arc into its basement throughout the early Jurassic. We also did detrital zircon. I'm not showing a lot of that data. There's a lot more data than this one plot I took. The key point is that everything we find in detrital zircon, we can rationalize with the local geology. So we don't have to look at exotic sources for any of the clasts or zircons into the Whitehorse Trough. It was basically the shoulder we're exhuming and dumping into this axial trough. It's probably a bit hard to see, but the Aftium data here, the circles show the range of some of the plutonic suite I talked about. So there's a pretty clear overlap there. This was a series of diagrams that I've put together just by combining fossil ages and MDAs. I should point out that wherever we had detrital zircon from strata that we knew the age from fossils, we have good confidence that MDAs in those detrital zircon are actually representing the age of the strata. So we compiled this, and this is the infill pattern that came out from this data, where this is very similar to. I was reading at the time some paper on the Dead Sea, where the infill pattern in the strike slip basin there is very similar. So that that line of argument has led us to think that this was probably a strike slip basin. We speculated on all sort of different interpretation prior to this study, but I think that's probably the most consistent pattern that we see. So all the stuff I've been saying is basically we have synccollisional granites that are progressively getting younger in Yukon, in this part here of the system. We have evidence of amphibolites facies metamorphism, burial, and followed not too long afterward by exhumation in the early Jurassic. And at that time, we also developed this basin that we think was probably in the strike slip system, the Whitehorse Trough, which received the sediments from that exhuming infrastructure. So all of this goes well until we hit the Stickeen Arch, which is an uplift, which is where there are upper Triassic strata sticking out. If we go down in British Columbia, what we see is at the same time is that we have the Hazelton group is being deposited. And Joanne Nelson and her colleagues at the BCGS were able to document that the earliest magmatism in the Hazelton is about 203 near the Stickeen Arch and seems to get younger as you go southward. That led Joanne to suggest that this was a retreating arc system that was moving southward, that was retreating southward through deposition of the Hazelton, and that this area here north of Stewart was basically the back arc to the system, and this is what explorationists would refer to as the Golden Triangle, which is an area with very rich porphyry copper gold deposits. So in essence, we have a system retreating arc. We have a strike slip system, so a strike slip control system in the collisional zone to the north of that. So where does that leave us? The prevalent or the main model that's been proposed for the geometry that we see in the Canadian Cordillera was proposed by Mitch Mihalonok and colleagues at the BCGS, that this was an oroclino enclosure of the Cache Creek terrain. The trigger was thought to be the arrival of those Cache Creek seamounts into the subduction zone that basically cause counterclockwise rotation of Stickinia in the Jurassic. And then by middle Jurassic, everything gets imbricated, and then that's the end of that story. I've more recently proposed an alternative in which what we see is an anon arc collision starting in Sinimurian, where basically it's North America that's encroaching onto this system and causing the collapse of this arc system in Yukon. So we're having crustal thickening here to the north, while the Hazelton Trench or arc system is retreating southward at that time, and that leads to development of this transform system that feeds into the collisional zone to the north. By the middle Jurassic, we have full imbrication of the system, and that's when we have slab breakoff or foundering of the slab, which result in a stenospheric upwelling and more juvenile magmatism of the Bright Sweet that I mentioned briefly earlier. All of this leads to uplift and exhumation of this part of the system, and that's recorded in the younger sediments in Yukon, the Tantalus Formation, which is for the most part Oxfordian to lower Cretaceous. Possibly could be a slightly older. Some DMDA suggest that could have started in Battonian, but in any case, these deposits are sandstone conglomerates and coal that have been interpreted to be deposited in confined valley in a mountainous region at that time. So that's the main story. If you're good to stick with me for another 5 minutes, then I'll show a few relationships that I think are critical to Cretaceous tectonism in the Northern Cordillera. Is that okay, Sarah?
Yes, please continue.
Okay. So, so all the intermountain terrains, then they are basically transported and overlapped the western continental margin of North America. So this is a seismic section. Just you barely see Yukon terrain, but it's right in here. It's just a thin skiff sitting that overlaps rocks that are thought to be North American margin. We would probably draw this section slightly differently today, but that's okay for now. So the leading edge of that whole system is the Inconnu Trust. So let's go look at the relationship along the Inconnu Trust. What do we know about its timing? In this part here, the Inconnu Trust, which is here, basically is trust slide mountain Yukon rocks on top of late Triassic, upper Triassic sedimentary succession, Norian mostly in this region. If we go, then the minimum overlap we can argue for here, because this is a clippa of Yukon is probably about 25 kilometers, perhaps more. If we go to the northern part of the Inconnu system, we see similar things. We have upper Triassic in the footwall. There's some upper Triassic imbricated with slide mountain rocks. But the key relationship is here when we track this fault here, and I've blown up that portion here just to show that this is plugged by the Orcape Atlet, which is roughly 100 million year range in age, or 104 to 96. We'll call it 100 for our purpose. So basically, the overlap of Yukon with North American rocks is Jura-Cretaceous in age. We can look at, and here, just to show that this is just a flap, there's a window of Triassic and other rocks here in peeking up from beneath Yukon might give you a 30-some kilometers of overlap, perhaps less if this is a piece of this imbricated slide mountain Triassic rocks. Okay, let's go look at another zone here, the Tumul zone on the other side of the Tintina Fault. This is a steep panel of slide mountain rocks, the same kind of slide mountain rocks we could see on the other side of the Tintina Fault. It's only about a kilometer in width in this area, and that's a steeply dipping panel. I think that was probably originally a thrust imbricate that was modified by later strike slip displacement. It could be that the whole thing is strike slip. In any case, I'm going to zoom into this area here where a student did some pretty good detailed work and was able to map previously unknown Cretaceous plutons right in the middle of that fault zone. And also mapped an Andalusite oriole that goes right across the whole area here. So I think this structure here is plugged by 103. Before I leave the slide, I'll point out that this is Solitary Mountain, infamous site for paleomagnetic study of the Carmacks group, the easternmost Carmacks in Yukon. Okay, the last one I'll look at, because this is a nice area to look at. This is the Sylvester Alocton in northern British Columbia. And again, imbrication of Yukon and slide mountain terrains sitting as a clippa on top of Devonian carbonate of the continental margin here. Again, if we look at this, the Cassiar Batlet, about 114 MA, plugs the backside of that Sylvester Alocton. So that structure is plugged by 114. So conclusion, we have the intermountain terrain are glued to North American rocks by 114 to 100. So the other set of, so you can say, well, okay, I talked about this boundary here, this one here. But that's glued to Cassiar terrain or extension, the other side of the Tintina Fault, which is McAvoy platform. What if we have displacement along this structure? That's entirely possible. This is a slide from Hugh Gabriel's. So, we can restore this segment here is about 430, 490 kilometers of displacement in mostly Eocene time. But Hugh Gabriel had long suggested that there might be displacement, Cretaceous displacement along the northern Rocky Mountain Trench to realign facies in the Cassiar platform with the southern end of the Kichika Trough, which is this kind of stipple pattern here. You could probably even take this further if you want. And a colleague at YGS is kind of investigating this idea and saying that, well, if you want to really restore everything, then you have to bring back the McAvoy platform to that point as well, which could give you up to close to 1,500 kilometers of displacement. So there we go. We're talking about large-scale displacement. Although if we look at that structure here, this is what it looks like. This is the boundary between McAvoy platform and Selwyn Basin, and it's plugged by a 105 battlet. So all of this brings it to a head again with the paleomag for the Carmax group, which suggests large-scale displacement post 70 million years. I don't have an answer for you on how to explain this. This is not the point of what I'm trying. I want to just show that there are solid relationships that need to be acknowledged, that are mapped relationship that are completely at odds with a model like what Basil has proposed here. There is no gap between this. This matches with this matches with that, and there are Cretaceous plutons that plug these two systems together. So those Cretaceous plutons, this is my last slide. Those Cretaceous plutons extend far east into Selwyn Basin in Yukon. They're extending quite a bit east in southern BC into the western Rockies, the western main ranges of the Rocky Mountains. So some people have suggested, well, let's put the suture on the other side of these plutons, or even at the truss front, at the origin front. If you want to do that, then you have to contend with the stratigraphic relationships that are beautifully outlined in this geology paper by Margot McMicken. I won't get into those details, but I invite anybody to look at that study very closely before making a model. So that's all I have to say.